Good morning all. Welcome you to the Radiological Equipment lecture series. We are discussing about the unit 5 ultrasound transducers. So in this unit we are going to discuss about ultrasound beam properties. So initially we have covered what is ultrasound transducer, how ultrasound waves are produced from the transducer and what is the principle behind this, and how piezoelectric effect plays a major role in producing ultrasound waveform. So here we will discuss about the beam properties. Let's move on to the first slide. So here I have given a simplified model and an accurate model for your understanding. So first we will discuss about the simplified model. The black color dark rectangle over here before the number time 4 is a piezoelectric crystal for your understanding. Lambda represents the wavelength of the sound wave produced from the piezoelectric crystal. So when the crystal vibrate, we have already explained how the compression and rarefaction are produced. And in the accurate model, which is just you see on the screen, having 4 dots over there, and each dot represents a piezoelectric crystal. Usually ultrasound transducers will not work with a single crystal or a single piezoelectric crystal. So it will have n number of crystals in terms of multiples of 2. For example, 2, 4, 8, 16, 64, 128, 512, like that. So it will have n number of crystal in a linear, it is arranged in a linear fashion or curved fashion or three-dimensional matrix fashion according to the transducer and the need of image acquisition. If we have more than one particular piezoelectric crystals or which is like what you see in the diagram, if you have 4 or 5 numbers together, and each crystal will be excited with the help of voltage pulse, and during each vibration produced by the crystal, ultrasound wave will be transferred. Each crystal will oscillate and each crystal will produce an ultrasound waveform. When these waveform move together in one single direction, in the same direction, it will combine together at a particular distance or a point. And here we are going to see how this construction and destruction interferences, we call that as technically as construction and destruction interferences. If the waveform have same kind of wavelength and it join together, then we call that as a constructive interferences. If it is different to each other and it will join together to cancel out each other waveform, we call that as a destructive interferences. So how this property is going to help us for better imaging using the ultrasound transducer, we will discuss. As you see here, we have two diagrams labeled as A and B. So A is a point source waveform. When a crystal is vibrating, we will have a concentric circle around that particular crystal. Like when you drop a small stone in a still water or a pond, you could see a wave which is formed and which is been traveling away from the point where you have dropped the stone. So like that, the next to the picture A, towards the right side of that, having 2 points of the same. The A picture represent when one stone is dropped in the water, how the concentric circles are formed. The second picture explains when 2 stones are dropped simultaneously at the same time in a still water, how the concentric rings are formed. Like that, when you increase the number of stone dropping in the still water, how many concentric circles will form and where they are going to meet together to have a strong numbers. So like that, the point B represent an ultrasound transducer with n number of piezoelectric transducers which is aligned in a linear fashion, and when all these crystals get excited at a same time, you could see that all the transducers or all the crystals will start vibrating and producing concentric sound waves or circles in the same time, and it will going to travel in the same direction, and after a certain distance all these concentric circle which is going to have a common meeting point where the strength will be maximum than the point where it is being produced. We call that as a line of focus, and the point from the transducer to the line of focus is called as a near field, and the point away from the focus point or the middle point is called far field. So we are going to divide the beam characteristics into two different types. One is the distance from the center point, that is focus point, to the or towards the transducer is called near field, and from the focus point away from the transducer is called far field. So we have certain formulas to describe what is near field and what is far field, and here we have two pictures, picture A and picture B. Picture A represents the transducer element which is having the crystal of diameter D, and if the diameter of the crystal is taken as D, the length of the near field could be calculated with the same formula, and r square by lambda, or we can use d square by 4 lambda. So lambda represents the wavelength of the sound wave produced by the crystal, and this gives the length of the near field. And if you want to calculate the length of the far field, we have to use sin theta is equal to 1.22 lambda by d. D represents the diameter of the piezoelectric crystal, and lambda represents the wavelength of the sound. So with these two formulas, we could able to calculate what is the length, or what is the number of near field, what is the number for far field. And you could see that the picture B represent pressure amplitude variation. When an ultrasound transducer start vibrating, it forms a concentric circles like sound waves, and it start traveling together in a same direction. When it obtain the middle or the focal point or the center region, it will be stronger, or it will be much focused than where it is being produced. And when it is leaving that focal point away, or it is whenever it is traveling away from the transducer for larger distance, then these concentric circles start dissolving. So till the near field, we could able to have a good spatial resolution when you are acquiring, or when you are using this kind of space for acquiring images. So, and if you want to use the same ultrasound transducer for therapy, and which for the application of larger distance travel, we could always prefer the far field. That is, when you are, according to the application, we will choose whether the transducer has to be operated in the near field. For example, if you are scanning the organs or the region very near to the skin, or very much not distance away from the surface of the skin, then the near field is acceptable. And if you are going to scan the regions, like if you are going to scan the kidney and it is far away from the surface of the skin and the abdomen, so we are going to depend on the far field. So according to the application and according to the imaging, we are going to choose whether it has to be operated in far field or near field. And thank you for listening. I hope this video gave a small idea about what is the beam characteristics of ultrasound, and what is near field and far field, and how these fields are produced, and for which application or what kind we are going to use the same. Thank you all for watching.